So my talk's a bit different from the ones that have gone before in a couple of respects. One is that we're building it now, and the other is that I've got to cover a calorimeter that incorporates electromagnetic and hadronic parts in the same time that Vincent had for electromagnetic and Jamal had for hadronic. So it will be quite highly granular, my talk, as well as the content. Firstly, why are we doing this now? To give you a bit of a background, and it's, why are we upgrading the CMS? Why do we need to change? And it's all to do with the LHC, of course. So at the moment, we can cope with the instantaneous luminosity and the radiation damage and the pileup that comes with it with the existing calorimeters of CMS. The same with Atlas, of course. But for the future, when we go to this higher luminosity phase of LHC, where we go up by a factor of about 5 in instantaneous luminosity and a factor of about 10 in integrated luminosity, the existing calorimeters will just die. So we can't cope with that. So with the physics that we want to do, this gives us an opportunity as well to change the calorimeters to something that is really tuned for good jet identification and measurement. This is really where we want to go to. So to reiterate, the things that hurt the present calorimeter and that are quite different from CPC or ILC is radiation. And it comes in two forms. One is the damage that it does to your detector. So we're reaching in the hottest part of the end caps, and it's the end caps I'm talking about, of course, in CMS. A neutron fluence of about 10 to the 16, which is the same as what you get in the inner part of the pixel detectors. So neutron fluence is massive. And then the pileup is the other thing. So this is a real CMS event from a few years ago where where the LHC deliberately went for high pileup, and we got 78 simultaneous or nearly simultaneous events. And high luminosity LHC, we're going to go up to about 200. So things get really complicated. One thing to point out is that this picture here in the end caps is the replacement calorimeter, and the neutron fluence varies by about 5 orders of magnitude over that end cap. So this is the part of CMS we're talking about, the end caps. These are the present detectors. We have an electromagnetic calorimeter and a hadron calorimeter, and they'll both go. So, of course, the starting point for the upgrade has to be that we need something that's radiation tolerant and able to deal with this pileup. And then we want to benefit from technologies that largely actually come from CALIS to make an overall detector improvement. And one of the biggest challenges, as I said, is jet energy resolution. So this morning we heard about one way of possibly improving jet energy resolution using dual readout. So there were quite a few talks on that, so you can refer to that. I won't go into detail on that at all. And the other way of trying to improve the jet energy resolution is the high granularity way, and that's the one we've chosen. So both have their pros and cons. We've chosen the HG-Cal, and of course the objective is to build a particle flow calorimeter, where the idea is that now, instead of a calorimeter just being something that measures energy, it works in harmony with the tracking and with the muon detectors to try and get a full picture of what happens in your showers, in your jets, inside the event as a whole. So you have your jet energy sum, for example, is now based very much on what the tracker tells you, and also what the calorimeters tell you, for the neutral parts in particular. So particle flow is not really anything new. Building a particle flow calorimeter from scratch is new, but the techniques have been used in CMS and in Aleph and Delphi in the past with a lot of success. And these plots are just illustrating the difference in CMS if you just use standard sort of techniques to reconstruct the energy of jets, or if you use particle flow techniques, that's the red. So there's massive improvements. Similarly on the right for measuring missing energy. with a particle flow calorimeter, it turns out that actually granularity is more important than the absolute energy resolution. And the lateral granularity has to be below the Mollier radius in both the ECAL and the HCAL to be able to profit from the granularity. And this is especially for making good two-shower separations in this horrible high pile-up environment in the end caps especially. It should be noted as well, no one really talks about this. For really good particle flow, you need really good software. So you can build the best detector you like, but without the software to go with it, it doesn't work. And I'll come back to that later, actually. I used to have, in other versions of this talk, I have a quote on here from the spokesperson at the time when CMS chose this calorimeter. And he said, "There are no showstoppers, it's all just engineering." And I loved the quote, "just engineering." I think this is probably the most challenging engineering project we've ever undertaken in particle physics. I'm a bit biased, of course, because I work on this. So where do we start? Well, we start with identifying materials to use. They have to be radiation tolerant. We have to have on-detector electronics. We have to have high bandwidth data transmission. Has to be low cost as well, or relatively low cost. Nothing in CMS is really low cost. And then powerful FPGAs for the off-detector electronics, just like everything else. So, as I said, we start by looking for radiation-hard materials. And then we go from there to build these detectors. We need to select the right materials to use as absorbers and so on to make the small Mollier radius. We have to make it as dense as possible. So what we've come up with is that we use mainly silicon. So silicon sensor-based sampling calorimeter with various absorbers. So we've looked at tungsten, lead, copper tungsten alloy, stainless steel. And this is followed, so longitudinally, if you like, by plastic scintillator tiles with direct SIPM readout, as Jamal has just described, very similar to the Calais HCAL, for the lower radiation level regions. Remember, there was this 5 orders of magnitude across the whole NCAP, so we can profit from that and use silicon where we need to use it, but don't use it where we don't need to use it. With the silicon and with the scintillator, then you need to figure out what granularity you need. And this actually comes from the need to calibrate, and we calibrate with MIPS. So we need a good signal to noise for the MIPS after 3 inverse attobans of radiation damage. So we want low capacitance silicon cells, which sets the scale of the area to be about 0.5 to 1.1 centimeters squared, and scintillator cells with small area, which is about 3 by 3 as well. We need to have the fine longitudinal sampling, so you get a reasonable energy resolution. It doesn't need to be world-leading, but it needs to be reasonable, especially because we've got very thin active layers. So this is our plan. We take the present NCAPs of CMS, and we cut them off, almost literally, and you lift the whole thing to the surface, where you have a pre-built high granularity calorimeter that you lower down and attach to the existing NCAP yoke. So that's the concept of all of this. And this is the transverse design. So everything you see in green is a layer of silicon sensors, and everything you see in blue is scintillator. So you can see it follows a line, which actually I'll show you in a minute, of radiation damage. So silicon where you really need it, scintillator everywhere else. We have about 600 square meters of silicon sensors, which is 3 times the present CMS tracker. So it's quite a large amount of silicon. 500 square meters of scintillator as well. And all of this has to operate at minus 30 degrees to mitigate the damage to the silicon. So the whole thing is cooled to minus 30. That actually gives you some good things about it as well. It means you can have these mixtures in layers between 2 different technologies, which is quite nice to have. give you an idea of what this gives you in physics. It's just one example event, which is a Higgs to gamma-gamma from vector boson fusion. So it has a high-energy jet, and that jet has 3 leading particles, 2 pions and a gamma, and there's another gamma in there as well. And these are all incident on the end cap. And what you see in the various layers is you start to see 2 signals appear. So these are from the 2 photons. One is from the isolated photon, one is from the photon within the jet. And then towards the end of the electromagnetic section, they've died away. But then you go into the hadronic section, and then things start to appear again. So you see the rest of the jet. So you start to see the pions from the jet as well. So this longitudinal granularity can really help you understand what's going on in detail in a jet. This just shows you again that we've mapped out the different regions because of the radiation. So a couple of things on the silicon. So we've chosen to try to be as cheap as possible, which means planar P-type, well, not as cheap as possible. DC coupled sensor pads, we've chosen P-type as baseline because it's more radiation resistant than N-type. We may use N-type in some of the lower radiation regions of the silicon part. We use hexagonal silicon sensors, which I'll show you. We preferred to square because you use more of the area of the silicon wafer. And we want to use big wafers, which is 8-inch, which reduces the number of modules, which means you reduce your assembly time. And we use different thicknesses of silicon, which I'll come to, and it has to be all simple and rugged, of course. So why do we use different thicknesses? So this is a very complex plot. It has the signal that you get from the silicon as a function of neutron fluence. Okay, and we have on the left, this is for 300 micron thick silicon. And what you can see is that with virtually no radiation damage, you get a signal of about 15K electrons. And as you increase, it goes down a lot. And if you were to increase it further, you follow this dotted line. However, if you go to 200 microns, although you start off lower, it doesn't go down as fast. And the same is true of the 120 micron. So to reach really high fluences with a reasonable signal size, the thinner ones are better. This is a layout of one of our silicon sensors. So it's a hexagonal device, and it's divided into smaller hexagons. Of course, at the edges, they're slightly different shapes. They have to be to make a full hexagon. The different colors here are representing the trigger cells. So we combine individual silicon cells to form different trigger cells. We have 2 different designs. One is for the thinnest sensors, which will go in the highest radiation region where the highest occupancy is as well. So there's 432 cells in there, 192 in the others. And then there's some details of what it looks like. This is a real silicon sensor that we made. This is only 6-inch as a prototype. But we were getting pretty good results. So we were getting of the order of nanoamps per cell, which is extremely good before radiation damage, and very uniform across the whole hexagon. And there are some special cells in here that can facilitate calibration as well, which I can talk about later if you want. A silicon module essentially is built on a dense base plate. We're actually using copper tungsten in the electromagnetic section. So it's an alloy, 75% tungsten, 25% copper, with a Kapton sheet that provides the bias voltage to the backside of the silicon, and then that's all glued to a PCB, a bit like Vincent described earlier. And then we have an automatic gantry machine here that's currently we've only got 1 of them in Santa Barbara in California, but there will be 6 of them around the world. If you look closely at this module, one of the novel designs of this is actually to try and make the connection to the silicon from the front-end electronics. And you can't use bump bonding because the size of the device is too large. So if you heat it up to do the bump bonding, as it cools down, it just cracks everything. So you can't use that. So what we've done instead is we glue it, and then we have these holes in there where we have wire bonds that go down from the PCB directly to the silicon. We also, one thing to say, we started with these modules having conductive glue on the back to go between the silicon and the Kapton to provide the high voltage or the bias voltage line. That is incredibly unreliable, and long term, and especially in radiation, it just doesn't work. So we'll do backside bonding as well to provide the bias to this. This is what a relatively, well, for us, relatively large prototype that we operated in a beam last year looks like. So this has 7 surrounding each other. Wonderful HDMI cables, similar to many of the CALIS experiments. I won't go into this. This is the latest version, or one of the latest versions of the CALIS AH-Cal, which Jamal has described in detail with a silicon photomultiplier and a plastic scintillator plate. And the procedures for this, one thing I did like to point out is that it's all automated now. So the wrapping of the tiles is automated, the placement of them, the gluing of them is automated, and so on. It's quite a fast procedure to make these things. The electronics, which I think Stefan will tell you a bit more about later, are very complex for the HG-Cal. They have to be low noise, they have to see MIPS, they have to have a massive dynamic range up to thousands of MIPS. For that dynamic range, we want to use 130 nanometer CMOS because it has a higher voltage supply than the 65 nanometer. We want to have precise timing information at a level of 20 picoseconds or so, which means you need a very good clock distribution. You need to have fast shaping, quite a long latency, so you need to have an onboard memory, and so on. And it needs to interface with common projects, which I'll show in the next slide. So if you look at a schematic of our front end, we're designing a couple of our own ASICs. One is the front end that I just described very briefly, and the other one is a concentrator chip. But everything else we're trying to use is a common CERN and associated institutes development. So things like the low power GBT link, the versatile optical link, and so on. So we try to use as much as we can of everything else. This is a picture that some things are starting to exist. This is just a mechanical mock-up of how we connect our hexagonal modules to the outside world through a second board that has all of these optical links, DC-DC converters, and so on it. And this is then what a cassette, a so-called cassette, looks like. So we started off, I'm going to need a few more minutes, I'm afraid, so I'm going to upset people by going over a little bit. We started off life looking at something very similar to what Vincent showed, which was like a carbon fiber alveolar structure where you slide cassettes in. For us, that wasn't the optimum choice. So we're actually having self-supporting cassettes where it's based around a copper plate that has embedded cooling tubes inside it, and that they carry biphase carbon dioxide to act as the coolant, and then you attach these silicon modules to either side of that plate. So they're in conductive contact, and that's what provides the cooling. And then you close the cassette with these big black things here, which are lead sheets, lead wrapped with steel, give it some strength, because otherwise the lead is floppy. And then you get a cassette, and then you have it this shape, and you can put them all together, and you get a nice circle. We've tested some of these things, so we look at the temperature difference across one of these quite big cassettes, and the scale on this is very small. So you can see it varies between 32.3 degrees and 34 degrees. So across a cassette, the temperature difference is virtually nothing. In some parts of the detector, you also have the scintillator part. So there's what we call a mixed cassette, which is very similar but a bit different. And then this shows you, this is what a silicon one looks like. This is what a mixed one can look like with the scintillator tiles that vary in size as you go out. last couple of slides, I'll just show you a couple of highlights here. This is the biggest system we've tested so far in a beam prototype system, which actually uses a modified version of the Calis AH-Cal to add extra depth and to complement the silicon parts that we have here. So we have some silicon sensors here. It's about 2 tons, so it's quite large. We can see MIPS quite easily, not with the signal to noise that some others have shown you, but with a signal to noise of about 8. This is quite nice. This is also a MIPS signal from the Calis part, where the MIPS were not muons. These are MIPS seen within hadronic showers. So you can also calibrate using the MIPS from within the showers. And there's some event displays on the top that show you how the showers progress. We haven't had a full complement of layers yet, so we can't do ultimate performance, but we can match with simulation, and that gives us confidence that our simulation can be used to do the full design. And the shower shapes, things like the transverse shower shape for hadrons, matches very good with the simulation, which is excellent news. Time in performance we've also measured, and we can reach a constant term of about 20 picoseconds with the silicon. This is not with single particles. This is with showers. So this here is about 20 MIPS signal. So it's quite a lot. It's not a very big signal, actually, but you can, in principle, reach very good values if your electronics can deal with it. And then this shows you the advantage of having that time in information. This is with no time in cut, and you can hardly see the VBF jet and the gamma. Adding the time in cut shows them up straight away. This is kind of the expected Higgs to gamma-gamma performance, which isn't bad. It's comparable, actually, to the present end caps of CMS. So even though the stochastic term of the energy resolution is around 25–30%, the overall performance is not very far different from what we have at the moment. I won't go into the ID. Last thing. Well, we've finally got our TDR out very recently, just a month ago. So now the real work starts. We need to finalize the design, finish the prototyping, head towards EDRs, do market surveys, and start production in less than 3 years. So this is really a short time scale because we need to install this thing around 2024. It's a major challenge just to get this thing built now. And we haven't finished the design yet. Thanks.
Thanks so much, David.
Sorry for going over a little bit.
Okay, just not 2 minutes. That's fine. Questions, comments?
Thanks. So I'm wondering, because you're going to use 130 nanometers technology, whether that technology is qualified for that high radiation hardness?
I mean, the tests we've done so far with things like the pixel chips and so on seems to say, yes, it is. Actually, it's not any worse, really, than the 65 nanometer, and is a lot easier to deal with than the 65 nanometer in various ways. Firstly, the design is much easier, and the operation is a bit easier as well. So unless you really need a compact chip, there's not much gain to be had by going down to 65.
Sorry, I have a second question. Are you going to continue the 8-inch prototyping?
8-inch is our baseline. So we are producing 8-inch sensors in 3 different manufacturers. We already have prototypes from all 3.
We just lost one, right?
Sorry?
We just lost one important one. And
we may really have just lost one, yes. We're not sure yet. They may have priced themselves out of the market. But we keep in the best one.
Other questions, comments? Okay.
Yeah, I think that's the right thing to say.
Thanks again.